Hello, my name is Patrick Gavigan. On behalf of my supervisor Babakis Fendiari and I'd like to talk to you about BDI for Autonomous Mobile Robot Navigation. So our project is about doing a navigation framework for BDI agents. Now there's current approaches for solving this type of problem, and certainly there have been other projects that have shown the feasibility of using BDI agents or belief, desires, intentions agents for controlling different types of mobile robots such as UAVs and cars. They tend to be tied to specific implementations, so specific agent implementation tied to a specific type of UAV or a specific type of robot. Now, certainly there are projects that link the robot operating system, for example, with JSON as a means of sort of trying to generalize things out. But what I'm noticing when I look at the related work, and certainly I invite you to look at the related work section of my paper, we tend to see that the role of the agent is a little bit more limited. They tend to call out to other nodes or other types of routines for performing the navigation type of activity. Perhaps that's out of an underlying belief that the agent isn't sufficiently capable. An example of one of those external modules could be something like MoveBase, which is very popular in the ROS community for dealing with the navigation type of problem. Now our approach turns this on its head a little bit. We want to look at this from the perspective of getting the agent to do as much as possible. Can we utilize the reasoner for monitoring the plan execution? Can we use that reasoner to make decisions based upon where the agent is moving and where it is on its goal? And we're looking to seek any particular advantages or drawbacks to this type of approach. And of course, we're gonna compare some design approaches for doing this. Now, the components of our framework are threefold. We've got our agent speak plan as a route. We've got our turn-by-turn module, which is how we guide the agent between its waypoints on that route plan, and we handle interruptions. We're going to compare three different design methods, and we want to compare like with like, so we're going to do our route generation using the A-star algorithm. We've got an agent speak implementation, which we're using from Jason's implementation, a very nice piece of agent speak code. As well as an internal action and environmental module versions using the Russell and Norvig A-star implementation in Java, as well as a Python implementation of the A-star search. We've got three test environments, a synchronous and an asynchronous grid shown in the left, and we've got an air sim simulator for a car in a neighborhood environment shown on the right figure. So as I mentioned, we've got three main components to our navigation framework. We're going to dig into the behavior, and we're actually going to bring it down a little bit lower level than just looking at those high level three components. But first we're going to start with interruption, plan interruption. Now, typically when you write a belief, desires, intentions program, you're going to trigger on something, and often when I write these types of programs, I like to have everything trigger on achievement goals. But for our interruptions, we're going to do things a little differently. We're going to trigger on beliefs. That is, when you acquire a belief of something that you need to address right away, that's when you're going to trigger to deal with that. By contrast, for our navigation mission and our waypoints, which we'll talk about shortly, these are going to be achievement goal based. And the reason why we separate this out is because we now no longer need to put our interrupting beliefs as context checks in every one of our other plans. We've separated those responsibilities. Now you can focus on your navigation or focus on moving through your waypoints. And so in this plan here for navigation, we're going to generate a route, and in this case using the A-star in agent speak, but our other implementations use similar calls. And then use the route to set a set of achievement waypoints. The map definition is incredibly simple. And this is one place where agent speak really shines. You can symbolically define your locations and their coordinates, and then a possibility to move between those locations. If you need to update the map, it's as simple as adding or removing beliefs from your belief base. In the turn-by-turn module, it's the implementation of the waypoint. How do you move between locations? And really all you have to do here is implement some sort of a movement action that is specific to your particular robot. For the grid agents, it's as simple as saying move left, move right. For the car, it's going to be more complicated, and we'll get to that in a moment. For map updates, you're going to, in a situation, for example, where you arrive at a wall that you didn't know was going to be there, or you got a closed road, for example, you need to simply update your belief base. You drop the belief that it's possible to move between those locations. Now, if that was part of your route, you need to drop intentions. You can use a mental note about your destination and then simply readopt the achievement goal of navigating to that destination. So the grid agent, a little bit more detail. It's a 4x4 grid. The agent starts in the bottom left and is given the goal of getting to the bottom right. We tell it about most of the obstacles, but I don't tell it about the pedestrians, and I don't tell it about this particular obstacle right here. So it's going to need to do a map update. It's sitting on top of a battery charging station, and the agent can perceive its location, coordinates. It perceives obstacles, pedestrians, at least those that are in adjacent grid locations. It can perceive the charging station and its battery state. It moves by simply using move command, move left, right, and so on. And it can connect and disconnect from a battery to recharge it and honk a horn at pedestrians. The synchronous version is a very simple JSON program with the environment being updated, perceive, reason, act, and environment update. The asynchronous version separates things out with ROS. We're going to have ROS nodes for the environment and the sensors all updating themselves in their own time, with the reasoning system also operating on its own thread, its own process, and receiving perceptions through a perceptions topic. For the car, similar to the grid agent, we've given the car the goal of driving to a destination location. We think this is a more realistic environment than a grid. And for sensors, we've given it a compass, a GPS, and a speedometer, and it can set its steering wheel setting, and it controls a throttle and a brake. And in fact, I've also integrated with some fourth-year project students that we have at the university, have done some work with LiDAR and lane keep assist, and as an experiment, I've actually integrated with those as well as a little side project. I'm going to show you a video of that in a moment to see the car dodging obstacles. So as I mentioned, the synchronous agent is a very simple program. We've also given it internal actions for get path and a map in the environment. That's for the internal action and environmental module versions of navigation. And we look down to the synchronous version. We've used our SavvyROS BDI connection system for connecting the agent to ROS, where it's going to publish and subscribe to the perceptions and actions topics, as well as inbox and outbox and performance logging. The environment is connected to a translator through various topics with its sensor information and for actuation control. And that translator is going to convert that information into predicate style agent speak for perceptions and actions for the agent to control the environment. The car architecture is basically the same thing. Just our sensors and our actuators are a little bit different. And so here we have a GPS, a compass, and a speedometer. And for controlling steering, the agent actually controls steering manually, but for the speed control, I found it a little bit more straightforward to use a feedback control law. And so we use feedback control law to control the steering and the brake. It kind of works like a cruise controller. There's also internal actions for range and bearing. That's simply because we're working with latitude and longitude coordinates, so simply doing the math. So looking at the grid, noticing waypoint in red at the bottom, we're going to get to that in a moment. That's where we control the agent's movement. But at the top of the screen here, we've got pedestrians as an interrupting, belief-triggered plan, and simply honks the horn. If you're honking the horn, the agent's not moving. And then the pedestrian will hopefully get out of the way, but if it doesn't, you'll sit and just keep honking your horn. The battery state, if you have to recharge your battery, also belief-triggered. And in this case, though, it's a little more complicated. You need to drop your intentions associated with performing your regular navigation mission and adopt a new achievement goal of charging a battery. Once that's finished, you can readopt your navigation mission, navigating to the final destination. Managing your battery is very straightforward. You just simply navigate to a charge station, dock, charge the battery, and then this plan triggers recursively, and then disconnect when finished, and then continue with your mission. Waypoint is how that agent's going to move between those locations. Now here it's very straightforward. You simply move up, down, left, or right. And so we used rules for defining those directions. Now for the car, you would think it would need to be more complicated. At least when I started programming this, I was thinking it was going to be more complicated, and it ended up actually being fairly straightforward. Because what we do is, again, implementing waypoint shown in red as that key low-level piece to how that behavior is going to be implemented. But here what I did is I separated out sub-achievement goals for controlling the speed and controlling the steering. Now here I'm showing you how I controlled steering and speed with simply following magnetics. I actually also have done some work extending this to use lane keep assist and LiDAR for obstacle avoidance. But in this case, you simply control your speed, set the C to this desired speed setting in meters per second, and it controls the steering angle using relative compass bearing to a destination location. So let's see these in action. Bottom left is your grid. It's going to try to move straight across to the right. It's going to fail at that, so you'll see that there it goes, and it's going to change its destination. Now over here on the right, we're going to see something really interesting happen. Using the LiDAR, avoids the car, collision avoidance. Now that agent has honked its horn at its first pedestrian, if we're looking at the left again. It ran out of power, went back, charged its battery, and now it's moving through the grid environment. It's about to honk its horn at its next pedestrian. They get out of the way and back to its final destination. In looking at the performance of the agent, I looked at this in a couple of different ways. I logged the behavior and the actions, the types of plans that the agent was executing to get a sense of where the agent was spending its time, and also looking at the length of the reasoning cycle. So now if we look across the top of the figure here, we see the timelines. This is the full scale of the timeline, and underneath here I've zoomed it in so we can see some of those smaller timelines, especially for the simulated car where all the interesting stuff is happening in this tiny little space here. So I've spread it out a little bit. Figures across the bottom, we're looking at the reasoning cycle period. Well, let's start with the timelines. If we look at the synchronous grid, environmentally supported wins, followed by the internal action and the agent speak version. But let's look at the time scale. This time scale we're in milliseconds here. We're off by a handful of milliseconds in terms of the amount of time spent. Not a, frankly, very significant difference, at least not if we're considering this at the scale of what a user might notice. Now, if we look over at the asynchronous environment, such as our grid and our car, things turn on their head a little bit. The agent now needs to use some overhead of going through ROS to communicate with its sensors and actuators. Now, in this case, agent speak is actually the fastest, followed by internal action, and then environment, which is the slowest. That's also the case here with the simulated car. Agent speak's the fastest, followed by internal action, and then the environmentally supported. Now, if we look down here at our reasoning cycles, we see something else that's interesting. First, the mean reasoning cycle period stayed relatively consistent. And yes, this one looks a little bit different, but if you look at the scale, frankly, we're within milliseconds. That's very competitive. But if we look at these outliers, things start to get different. We'll notice that the internal action agent had the longest outlier. In fact, that's from doing the navigation routine, followed by agent speak, and the shortest was the environmentally supported. That's the case on all three environments. Now, why is that? It's really quite simple. The internal action took the longest amount of time in a reasoning cycle to perform the navigation solution, followed by the agent speak, which went a little bit faster. But the reasoning system for the environmentally supported agent didn't need to wait. It was able to continue reasoning about other things, perhaps, while some sort of module out in the environment was cranking and dealing with generating a navigation route and navigation solution. And so that agent could have done something else in the meantime. In our case, it didn't, but if that's something that's valuable to you as someone developing an agent, that could be a feature that's really interesting for you. And so let's summarize things up a little bit. We've used agent speak for controlling an agent and performing navigation. And in fact, there's certain advantages of doing that. There's the monitoring features that come with using BDI, but as well as the simplicity of updating the map by simply adding or dropping beliefs and letting the reasoning system manage things for you. Certainly is attractive for use in mobile robotics, and we've shown a framework for using agent speak with achievement goals for your route and turn-by-turn module, and we've also talked about how we can handle plan interruptions. I've compared implementations in agent speak with an internal action and environmental module for generating our routes, and we've done this in three environments: asynchronous and asynchronous grids, building up to a more complicated simulated car with AirSim. As I said, in the asynchronous cases, which is most realistic for robotics, the agent speak was the fastest, with environmentally supported being the slowest, but these differences frankly are negligible for the user. Our peak reasoning period was shortest for the environmentally supported, system, and that's because you simply didn't have to wait. So you could have actually used those reasoning cycles for doing other things. And with that, I'd like to thank you for your time and open the floor to questions.